Welcome to Neil's Narratives. I am your host, Neil Morgan. And on today's premiere episode, The Big Bang. Thank you for joining me today on the first episode of a new project where I plan to discuss and explain topics that I find either fascinating or important to our story as a species. Basically, the universe and nearly everything in it. This series will begin with a brief cosmic journey from the start of the universe, leading to the formation of stars and planets, and then the development of life on our planet, and thus lead on to the incredible story of humanity. In the interim, I'd love to hear suggestions for episodes. It can be anything, and in this case, the sky is definitely not the limit. Full disclosure, I am by no means an expert in the subjects I hope to tackle. I take advantage of AI toolkits to help me research and present these topics. I've always been fascinated with the intricacies of our reality, our history, post and prehistoric. Most importantly, I love sharing information and found great inspiration from podcasts such as The Rest is History and Stuff You Should Know, among others. With all that said, I will no doubt make mistakes, and I welcome corrections. I hope you enjoy. In this first episode, we start quite fittingly at the very beginning. Today, we're exploring the birth of the universe, from the Big Bang to the formation of atoms. The Big Bang. The universe began somewhere between 13.8 and 14.5 billion years ago, in an event we call the Big Bang. How do we know that? Well, cosmologists observe how fast the universe is expanding today, and then roll the cosmic clock backwards using mathematical models, rewinding space-time itself, until everything condenses into a single, unimaginably dense point, the very beginning. So why the date debate? It depends on whether the universe has always expanded at the same rate. If the rate's been steady, then 13.8 billion years is our best guess, but new data suggests it may have slowed down or sped up at different points, meaning we might actually be looking at an older universe, closer to 14.5 billion years. Of course, these age estimates are only as good as the models behind them. The truth is the universe might be older still, or we might be off by just a cosmic hair. But for today's story, we'll stick to the timeline we know. The moment when time, space, matter, and energy burst into being. Despite the name, it wasn't an explosion in space, it was an expansion of space itself. At the first moment, all matter, energy, space, and time were compressed into a single point of infinite density. What physicists call a singularity. A singularity is essentially a moment so extreme and mysterious, the rules of physics throw down their tools and walk off the job. Very strange stuff. At time zero, the universe began expanding very fast. In less than a trillionth of a second, it ballooned from smaller than an atom to larger than a galaxy. We call this wild growth cosmic inflation. Formation of fundamental forces and particles. As the universe expanded, it cooled, forming matter and antimatter. At first, it was unimaginably hot and dense, a seething soupy broth of fundamental particles like quarks, electrons, and neutrinos. Let's dip our toes into the tiny, almost incomprehensible world of quantum mechanics just for a second. Quarks are like the Lego blocks of matter. They come in 6 flavours: up, down, charm, strange, top, and bottom, each with different properties that determine how they behave. When you group certain quarks together, depending on which flavours you combine, they form larger particles like protons and neutrons, the stuff that makes up the nucleus or core of every atom. Electrons are the tiny negatively charged particles that orbit around the nucleus. They don't just spin idly, they are responsible for an atom's personality. The number and arrangement of electrons shape an atom's chemical behaviour and determines how it bonds with others. In short, electrons dictate how chemistry operates. And then we have neutrinos, odd little travellers of the subatomic world. They have almost no mass, no electric charge, and yet, right now, billions of them are passing straight through your body without a trace. Totally normal, do not be alarmed. Neutrinos are notoriously elusive, but by studying them, scientists hope to unravel some of the deepest mysteries about the early universe. It is worth it to see what a neutrino detector looks like. They are otherworldly in appearance, an incredible feat of human ingenuity. Okay, let's pull our toes back from that quantum puddle and return to the baby universe, still expanding, still cooling, still becoming something else. As the universe expanded and cooled in the first fractions of a second, it wasn't just matter that began to form. The forces that govern everything started to peel away from one another, like ingredients in a cosmic broth. At the very beginning, all the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely merged into a single unified force. But as the energy dropped, they split off, each taking on a distinct role in shaping the universe. Gravity began pulling things together. The strong force glued atomic nuclei. The weak force handled radioactive decay. And the electromagnetism took charge of light and charged particles. These are the invisible rules of the universe. At this point, our Lego-like quarks combined to form protons and neutrons, but it was still far too hot for atoms to exist. Funnily enough, matter and antimatter should have cancelled each other out completely in the early universe. They are essentially mirror images. When a particle of matter meets an antimatter twin, they annihilate each other in a huge burst of energy. But for reasons we still do not fully understand, there was a tiny imbalance. About 1 extra matter particle for every billion antimatter particle. That little surplus is why anything exists at all. Without it, the universe would be nothing but light. No stars, no planets, no us. Some theories suggest that perhaps somewhere out there, an alternate universe exists where antimatter won, and everything we know is flipped. But here in our patch of the multiverse, matter reigns supreme. Primordial nucleosynthesis. About 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to begin fusing into atomic nuclei. Mostly hydrogen and helium, with trace amounts of lithium. But why these 3 particular fellows? Well, hydrogen, the most common element in the universe, comprising 75% of universal mass, is just a single proton or neutron with an orbiting electron. This simple combination meant it was the first stable atom to form. Helium is slightly more complex and came to be with the nuclear fusion of hydrogen atoms. Interestingly, this fusion only had a brief window of time of about 3 to 20 minutes, during which it was still hot enough for the process to occur before the expansion and cooling down period interrupted this fusion. Helium makes up about 25% of the universal mass. Following the trend, lithium had more of a complex construction and is less stable, and thus had a smaller window of time to form, as it is heavier than its counterparts. The early universe was, for a brief period of time, a giant nuclear fusion reactor, hot enough to form only the lightest of elements. This process is called Big Bang nucleosynthesis, which would make a pretty good band name. Heavier atoms would take billions of years to arrive under the mechanisms of nuclear fusion inside celestial forges that we call stars. Recombination and the birth of light. Around 380,000 years later, the universe had cooled to about 3000 Kelvin, or 2726 degrees Celsius. That's when electrons could finally combine with nuclei to form neutral atoms. This moment is called recombination. With charged particles now neutralized, light could travel freely. This light is what we see as the cosmic microwave background radiation, or the CMB. You can actually visualize the CMB by tuning an old analog TV between channels. Some of that static you see is partly composed of the faint afterglow of the Big Bang, and I for one am disappointed you can't watch the remnants of the Big Bang on modern tellies. The first atoms, the first light. Hydrogen and helium atoms floated freely in an ever-expanding universe. Gravity would eventually pull them into the first stars and galaxies, but that will come in our next episode. For now, we leave the universe as a vast dark place filled with glowing relic radiation and the simplest atoms drifting through space. From a single moment of violent expansionist creation to the first building blocks of everything we know, this is the start of our story. In the next episode, we'll explore how stars formed and forged the elements that make up you, me, and everything else around us. Thank you for listening to Neil's Narratives. I hope you enjoyed this first episode, and I hope to see you again. Thank you very much. Goodbye.